Let's see how much you remember your trig functions. That's the sine function, right? Vaguely remember the graph? So sine starts off at 0, goes up to 1, back down to 0, down to -1, back up to 1 or 0. The lines represent my slopes. So if we're looking at the slopes of those, what would this slope look like it's going to be? 1. That one. That one. That one. And what would be there? It would also be 1. Okay. And then if we went backwards. So what, if I was to graph that, what do you think it would look like? And what function is that one going to be? Cosine, because cosine starts off at 1, then goes down to 0, then goes down to -1. So just like that. Right? So if I'm looking at the slopes of sine, the derivative of sine is cosine. Now, yes, I could go through and do an actual proof out for you, but I think the graph actually makes it a little easier to see it. All right, so let's look at cosine. Because in essence, every single trig function that we have, you can turn into sines and cosines. Okay? So if we can find the derivative of sine and the derivative of cosine, I should be able to use those to find the derivatives of everything else. So let's look at the derivative. Let's look at cosine now. So this is cosine down here. What is the derivative at 0? What's the slope at 0? Or yeah, it would be 0, right? Does that make sense or no? I can draw a little line if you want me to draw a little line. So 0 there. What about here? -1. And then 0. All right. So what's, if I was to graph that, what do you think that would look like? So I'm starting at 0, right? And I'm going down to -1, correct? So I'm going down to -1, back up to 0, up to 1, and then back down to 0. So it's similar to sine, but it's flipped, right? So it is the derivative of cosine, I have it somewhere, is negative sine. Okay. All right. So we've got our two main derivatives. So what's the derivative of tangent? Well, what's tangent? So we only know sine and cosine now, right? So what is tangent in terms of sine and cosine? Sine over cosine. Yeah. Sine of x over cosine of x. So you can't just take the derivative of the top and the bottom. We have a quotient, right? So you have to use the quotient rule. So use the quotient rule that we talked about last Thursday. Those that don't remember. That's the quotient. Almost. Two little bit. One. Two negative positive. Cosine squared. Okay, so 2 seconds. These are both what? So that we look at it, right? And then the positive number. That's better. Don't worry. One of the things I was looking for. All right, so if we're looking at our pieces, we have f is sine of x, f prime is cosine of x, g is cosine of x, g prime is negative sine of x. So we have cosine of x times cosine of x minus sine of x times negative sine of x over cosine squared of x. So I have cosine squared of x plus sine squared of x over cosine squared of x. You cannot do that. You can't cancel on the top and the bottom unless it's multiplication. What's the cosine squared of x plus sine squared of x? Yeah, that's 1. It's one of your Pythagorean identities. So I have 1 over cosine squared of x. What's 1 over cosine of x? Secant. So this would be secant squared of x. So the derivative of tangent of x is secant squared of x. Yeah, I could sit here and make you do all the rest of them out if I wanted to, but I'm not. There you go. So those are the derivatives of our 6 trig functions. Cosecant, secant, and cotangent are all done the same way that we just did the tangent one. They're all quotient rules that we have to break down and simplify out. I will tell you that your index card for this test will probably be a lot fuller than your index card from the last test, because there's a lot of rules and things like that that you have to memorize. This also goes down to the more practice, the less you're going to have to memorize, because the more you'll remember. Okay. The biggest thing when we're looking at trig problems is remembering some of your trig identities. Pythagorean identities come up a lot. So remembering your Pythagorean identities, we're just going to pull up some of them, the ones that are important that you might want to remember. So you don't really need the cofunction ones, which you won't need. But the other ones you do. So the reciprocal identities, those come up quite a bit. We just used the secant one. The quotient identities for tangent, cosine, cotangent come up. And then your Pythagorean identities. You really only need to remember or know the first 3, the first row, because the ones underneath it are just rejiggerings of it. So like sine squared theta equals 1 minus cosine squared theta is just to remove it, change it, switching over. So like the first 3 are the ones that you have to remember, and then being able to manipulate them is important. So those come up quite a bit in these problems. Yeah. Not that often. So like the ones where you have, hold on, let's see if I can find. Yeah, I know which ones you're talking about. I'm trying to find the cheat sheet with them. Yeah. So you're not really going to use these as often. So these we really won't use that often because those have different variables in them. And most of the stuff that we're going to be dealing with is single variable. The ones that do happen to come up sometimes that aren't the ones that I just gave you is these. So this one here is the double angle formulas. Those will come up sometimes.
I meant the ones that distribute. So like if it's sine, right, x plus y.
Yeah, you won't use those. No, because again, they have multiple variables. So the vast majority of things you're going to deal with will only have a single variable in it. Or if it's going to have multiple variables, they're going to be like, it's going to be solved. It's not going to be inside of a function like that. So you don't really get into multivariable calculus until Cal 3, where you actually are dealing with the multiple variables in three-dimensional space and stuff like that. So we will a little bit when we do implicit differentiation with the x's and the y's, but those functions are very specific in how they're worked. And when we cover that, I think next class actually, we'll talk about those. So those are really the only ones those are the only other ones that'll come up would be like the double angle formulas. All right. Read this slide because we don't need those. Okay. Let's do one of these problems and then, or a couple of these, and then we'll move in to the chain rule, which is the biggest thing for today. Anybody taking physics? This is a physics problem. Object is fastened to the end of a vertical spring, stretched 4 centimeters beyond its rest position. The position at t time is 4 cosine of t. So that is the function we're looking at. I want to find the velocity and the acceleration. So velocity is what? First derivative, and acceleration is your second. So find me the first derivative of this and the second derivative. Oh, wait a second. Yeah. Oh, you're just totally get it. All right. One of the biggest mistakes I'm noticing in a lot of your work is parentheses. So f prime of t, a lot of people had this. Totally fine, except there should be parentheses there. It's not 4 minus sine of t. It's 4 times negative sine of t, which is really negative 4 sine of t. Don't forget your parentheses, because then it looks like something different, especially if you're going to use it again. Okay? Because if you had 4 minus it, then the 4 is going to vanish in the next step. And that's what I saw in a few people's papers. The second derivative of this would then be -4, and the sign becomes cosine. So that's it. All right, one more. Straightforward trig problem. Oh, okay. All set.
Yeah.
No problem. So find the derivative of 1 plus secant w, which should be w's, not x's. But so we get secant w, tangent w. The ones disappear because they are constants and they go. The derivative of g is negative secant w tangent w because just that negative sign stays in front of the secant. We plug them into the quotient rule. We distribute. The secant squared w tangent squared or tangent w's cancel each other out, so you're left with 2 secant w tangent w over 1 minus secant w squared. And there's no way to simplify that anymore. Even if I fold out the bottom, it's not going to make my life any easier.
If I left the second part, it would make it to the bottom. That partial credit.
Yeah. So you're typically going to have time to do that, though. So don't leave them like that. Huh? Oh, I make it so that it can be easily done in the hour or the hour and 45 minutes. So it's like, I don't try, like, believe it or not, this one's nothing compared to some of the other problems. um, these problems can get long. But so typically when I do the tests, when I create it so that it'll take me about 15 to 20 minutes. Assuming that means it's going to take you 4 to 5 times as long. Because I know how to do it and I know how to write it all out. So it should take me a lot less than you. It's funny, that's gone up a lot since I first started. Like when I first started, it was like I would double the time. Now it's like because I'm getting better and faster at doing them. So, but yeah, I designed the test in a way that you should be able to finish it no problem. Like I said, and I also come in earlier, so you do have a little bit of extra time if you think you're going to take longer on it. But all right. Do the second. Just do the first. Actually, no, I lied. I want you to do the second one, not the first one. Question is how do you get it? I'm just saying we were right then. Okay, now you had the warp covered up, so I have no idea how you went from there to there, but you did. Okay. I'm literally just seeing what everybody's trying. Actually, I'm happy you got it right. Yeah, it is. All right. Based on what you know so far, this actually is problem. This is one of the problems you actually can do, but you had to recognize one major thing. What's squared mean? There's two of them. So sine squared x is the same as sine of x times sine of x. Okay? That's important because now we have a what? We have a product. So you have to use the product rule. Okay? So to do the product rule on this, the derivative of sine is cosine. So we have sine of x, or actually, technically, cosine of x, sine of x, plus sine of x, cosine of x, which ends up being 2 cosine of x, sine of x. And that's the answer.
I ruined the way that I had.
Yeah, I think you had 2 sine of x, cosine of x, right?
Yeah.
That's fine. Yeah, it's still the same answer. Extra parentheses isn't necessarily a bad thing as long as they're in the right spots. So yeah, that would be the answer to that one. A couple things I did see I want to address so you can understand why those aren't. First of all, we can't just take the derivative of both of those and multiply if we get like cosine squared of x, because we have a product and we have to use the product rule. We talked about that last time. The other thing is that we can't necessarily do this and change it to 2 sine of x. That's like using the power rule, but that only works when it's just an x. Okay? Now, this problem actually leads us into, so because if I did write it like this, with the squared on the outside, this leads us to another problem that's actually, I'll say it. So if we had sine of x squared, some of you decided to change this to 2 and then cosine of x because you brought down the exponent. What's the only thing missing? The original piece, right? So this is close. The only thing we're missing is that. So if I took that and put it over here, I would have the exact same answer. That's actually known, there's a rule for that. It's known as the chain rule. The chain rule allows us to take a function that has basically a function inside of another function. So if you remember back to pre-calculus, when you were doing composite functions, remember the f of g of x was f with the g of x inside of that? So one of the exercises, depending on who taught it and how they taught it, but if they used ALEKS, one of the exercises was they gave you h of x equals this function, and you had to tell them what f of x and g of x was. You actually had to split the function up into 2 pieces. And at the time, most people, and depending on who taught it, they might have actually skipped over that because like there's no real purpose to this. The purpose is this. In calculus, we have two functions. We have what's known as the chain rule differentiation and then U substitution in integration. And both of those are taking pieces of a function and pulling it out of the function. So the chain rule takes the original function as the derivative of it, imagining the inside piece is a U, basically some other variable. And then it's the derivative of that extra piece. Okay. So that's basically what we just did in this last problem here. So if we're looking at, I'm going to just erase this whole thing and I'll rewrite it. So the original problem I had was sine squared of x, which I changed to sine x squared. So in this situation, if I make u sine of x, what is the derivative of u? That's cosine of x. What is the derivative of u squared? That's 2u, right? Correct? Because that's just bringing down the exponent, right? Yes, everybody good? Okay. So the chain rule states it's 2, u is sine of x, times the derivative of that. And that gives me my answer. So you're basically taking that internal function and turning it into just an extra piece that you're substituting. So this would be your 2 sine of x cosine of x. The other equation that I deleted a couple times was this. What's the piece that's annoying? The x squared. So this time we're going to make ux squared. What's the derivative of x squared? 2x. What's the derivative of sine of u? Cosine of u, right? That goes to that, correct? Yes? Okay. So the derivative of sine x squared is cosine of x squared times 2x. Or the better way to write it would be 2x cosine of x squared. So it's the derivative of the inside piece multiplied by the derivative of the function if that inside piece didn't exist. Okay. Out of all the things we've done, this is probably the most complicated and most confusing. It's probably more confusing than the actual quotient rule and product rule because those you can just plug things in and get the answer. We will do some more of them, don't worry. All right, let's look at one without signs, without tricks. So I've got f of x equals the square root of x squared plus 1. So what is the inside piece to this function? The x squared plus 1. So we're going to pull that out and make that u. And then I'm going to make f of u be u to the 1/2. That should do so good. So what is the derivative of u? What's the derivative of this? Oh no, what's the derivative of u? The x squared plus 1. That's just 2x, right? And then the derivative of u to the 1/2 is 1/2 u to the negative 1/2, right? I think is what you said. And we can change that to 1/2 squared u. So the question is, are we good on this side? Huh? Everybody understand where I got the u prime, the fu, and the f prime u? Yes?
Plug in 2x for two. Oh, you still, I'm confused where did the 2x go? Oh,
Nothing. We haven't used it yet. So the two pieces that we have to find before we plug back into the original problem is I need to find the derivative of u and the derivative of the function with u in it. So that's the u. I just basically took this piece out and made that u. And then if that piece was gone, that's what I have here. That's what that u to the 1/2 is. Okay? Now we're going to take that and we're going to plug it all back into the problem so we actually get the original derivative. So the derivative is u prime, so 2x, times that. So I have times 1 over 2 square root of x squared plus 1. So I can rewrite this as x over the square root of x squared plus 1. So this is u prime and f prime u. No, do not rationalize the denominator. That's okay. Yeah, it's not going to help you, and a lot of times it's going to make your problems a lot more complicated than it has to be. Does that make sense? The pieces? So just like everything else, do it in pieces. Don't try to do it all at once. And the notation that we're doing over here is going to help you when we start doing the integration later on and the u substitution, which is typically the more confusing and most useful piece of integration. Because in essence, we're going to do this again with the u substitution. So this notation actually comes back up a couple extra times. But yeah, this was that rule where it's like, okay, what's the function inside the function? So this was the problem from your pre-calc class. You just said, well, f of x is the square root of x, and g of x is x squared plus 1. And then that would have been f composed of g of x. That's literally why we do composite functions. It's for this stuff in calculus. So there was a reason for it all. You want to try this one? I'll give you one step that makes this a little easier. There. Now do the chain rule on that. No, that's why I changed it to that. I didn't want you to have to think, oh, I have to use proportional because it is. Remember, if there's only a one or something like that at the top, if I can move it up to the top to get negative exponent, it saves me that extra step. And I don't even know if I should be interchangeable. Later, yes, not now. Absolutely not. Good. I'll change that to you. I need to remove it. Um, Excuse me, like, good. So that's u. U prime is 2x plus 1. F of u is u to the negative 1/3. Prime of u is negative 1/3 u to the negative 4/3. Which if you want, you can change this to negative 1 over u to the 3u. Yeah. 3u to the positive 4/3. So f prime of x is 2x plus 1 times negative 1 over 3 to the x squared plus x plus 1 to the 4/3. So I've got 2x plus 1 negative over 3 x squared plus x plus 1 to the 4/3. So good. All right, try this one. I'm just looking across. Okay, yeah, I just want to make sure I wasn't down first. Oh, you make the video. Oh, beautiful. I think it's going to You got it. Keep going. Oh, yeah. So. What's your own? Exactly. Yeah. What happened to that? That's fine.
That's the.
Just replace the year. Replace the unit. So that goes with the units. And don't change the service. Obviously, then. Yeah. All right, the key when you're doing the chain rule, and actually the key that when you were doing the composite functions is, what's the piece that's annoying? Ask yourself that. What's the piece that makes this problem more complicated than the problems you've done before? The sign of x up there. Because you know what's the derivative of e to the x. It's just e to the x, right? So we know that. So, but that sign of x up there is kind of screwing me up. So get rid of it. Make it u. So what's the derivative of u? Cosine of x. So now I'm just doing e to the u. So y prime is e to the u. So actually, let me not put the y's there. So u, eraser, there we go. So y prime is u prime, so it's cosine of x, times e to the sine of x. And I'm done. Okay. So it's like, that's the key. It's like, pick out the piece that would be annoying. Pick out the piece that's causing the problem to be more complicated than it has to be. Make that your u, and then follow through your process. How do I do one problem before I do that crazy problem? Huh? Well, what do I do at the end of every class? When I'm basically done teaching you, and I start giving you problems that are more and more complicated. So there should be a pattern to this at this point. Okay, he's gone over the easy stuff. Now I get confused. Okay, just write the problem down. I'm going to help you through this problem. I'm going to give you another problem after this one that's similar, but slightly different. Okay, so in this problem, what do I have? Why do I have a product rule? I'm multiplying it, right? So I have two functions that are multiplied together. Now those two functions have exponents and other stuff around them, but in essence, I still have two things that are multiplied together. So I have f is the 2x plus 1 to the fifth. And then, which I need to find f prime. And then I have g, which is x to the third minus x plus 1 to the fourth, which I then need to find g prime. Right? Because that's how I do the product rule. Okay. Now, what makes this problem a little more complicated is how do I find the derivative of this? The 2x plus 1 to the fifth power. That I have to do the chain rule. Don't sit there and change it to 2x plus 1 times 2x plus 1 times 2x plus. You'll be here forever. But now we have to do the chain rule. Okay. So let's look at those. So in this problem, what's going to be my u? Huh? Right. The u is going to be my 2x plus 1. So u prime is what? 2. And then I have my f of u is u to the fifth, right? So f prime of u is what? 5u to the fourth. So that means this is 2 times 5, 2x plus 1 to the fourth. Right? Okay. Now you're on your own. So do G prime and then do the product rule. This you've got to do something to this. don't boil it all out, don't do any of that, just leave it in the base function when you get the product. Yeah, you can, so like, if you want, you can multiply that one.
Okay.
Just to clean that up a little bit, but don't.
Yeah. Alright.
Like the first one, I'm gonna multiply the 2 and the 5, so I got to provide 1 and 10. Like those little things are fine. But yes, like the only thing I would say is take that 10 and you can multiply that times that to clean up a little bit. Just to get rid of some of the parentheses, but yes, that's like that. Because honestly, at that point, the only other step is a crap ton of that. To boil out to the third power or to the fourth power. Like that's just a ton of stuff that you don't need. So this should be 3x squared minus 1 times 4 x to the third minus x plus 1 to the third power. So your y prime will be 10 times 2x plus 1 to the fourth times x to the third minus x plus 1 to the fourth plus 12x squared minus 4 times x to the third minus x plus 1 to the third times 2x plus 1 to the fifth. And you can leave it just like that. That's how I save you time of sitting there spending a half hour doing one problem on the test. Because I think the foiling all that out would probably take you 5 times as long as actually doing the step that gets there. And that's not what I'm testing you on. I want to know you know how to do chain rule, and I want to know that you know how to do the product rule. And my guess is that pretty much everybody, including myself, foiling all that out, we'd screw something up. Huh? But once you got that, it's literally just plug into the formula and you're done. So, all right. Okay, let's get this one. All right. How do you want to start it? Okay. So what's the inside?
Like, I mean, like you make him.
Okay. No. You're not. My question was, what would you do? you gave me a valid response of what you would do. Like, that's fine. Never assume because I'm thinking that you're wrong. Don't do that. Because part of what I'm trying to do when I'm teaching you these things is to start teaching you the one thing that unfortunately we forgot about in math a lot of times is thinking logically. It's like, okay, you've got a bunch of rules, a bunch of steps and everything else that you've understood and we've learned. It's like, now you start thinking logically, okay, I've got a new problem that I haven't seen before. Where do I go? Okay. And sometimes you're going to go completely and utterly wrong. That's fine. The question is how do you figure that out? Okay. And that's part of what I'm trying to get you to understand. So you're fine. Let's try that. If I make you tangent of x, right? So what would u prime be? Secant of x. Oh yeah, that's right. It's secant squared of x. That's that one. I have not memorized all these. I look them up almost every time I have to figure them out. So, all right. So we've got secant squared of x. Okay. So now that would make f of u sine cosine of u, right? What's f prime of u? So now we're like, okay, what do I do next? Right? So now the question is like, where do I go from here? So we kind of have to do like another chain rule now, right? We'd have to do the chain rule with u or with another letter being cosine of u. So this would work, but it's going to be very messy. Yeah. Yeah. Let's go one extra step out. What is the inside of sine? Is that cosine tangent, right? So let's go that direction. So instead of making u just the tangent of x, we're going to make u the cosine tangent of x. No, I saw. Wait. Yeah, it'd be negative sine. Yes, just give me a minute. No. I believe your answer is right, but you might be missing one little thing in what you said, but it very well could be that I just didn't hear it. All right, so now we kind of have to make this another letter. So if I do, let's make it w. So w is tangent of x. So w prime is secant squared of x, right? And then uw is cosine of w. So u prime of w is negative sine w, right? So this becomes secant squared of x times negative sine of tangent of x, right? Yes? And that's u prime. Now, f of u is sine of u. F prime of u is cosine of u. Correct? So f prime of x is secant squared of x. I'll put the negative sign out front. Sine tangent of x times cosine tangent x. I think I got a bunch of parentheses in there. I think I'm missing an extra part. There we go. Let me actually write it down below so it's easier to see. Negative secant squared x times sine tangent of x cosine tangent. There. So messy, yes. Totally admit, totally messy. But by making the U the whole thing on the inside and then doing it that way, it becomes actually a little less messy. I honestly believe if you did it your way, you probably would have gotten the right answer. It would have come out to be the same thing. I think it would have been a little messier in the second step. So it's just that's sometimes that's just the way you work it. It's like, as long as you're doing the math correctly, you can do a lot of different ways to get the answer. Some of them just take longer and become a little messier. And some of them you might go and it loops you back to where you started and it's like, okay, this isn't going to work. Let me try something else. And that's fine. That's totally an acceptable way to do math. As much as math teachers told you for decades, no, it's only one right way. This is the right answer. It's like, that's actually, believe it or not the way math works on the upper levels. Yes, 2 + 2 is always 4. And there's only one way to do that. But when you get up to the higher stuff, there's a lot of different ways to do it. So find the way that makes most sense to you, as long as you're using the right rules. All right, one more thing. What about this? Why? But we did e to the 2. We did e to the x. That was a variable in the exponent. Yes.
It's because 2 will be 0 for, right?
Well, remember, e is not a variable. E is a number. Right. So e in the way you're looking at it is e is a constant, so it'd be e to the x. So in your mind, this would be 2 to the x, not the actual answer. Otherwise, I wouldn't give it to you. There is a reason why e to the x works out to be e to the x. So let's actually look at something. Because this is something that you probably honestly don't remember. So let's look at just b to the x. So b can be anything, because I don't want it to limit it to one specific thing. Okay, so b can be any constant. It's still a constant. It's not a variable. The x is the only variable. But b can be any number. So can I do this? Would that be the same thing? But the question is why? So remember, so think about, if I'm going to do something, I have to be able to undo it, right? Okay. So if I took, so let's take this as 2 steps. So let's say if I did this, right? So ln of b to the x, so I've done something, now that's changed, correct? Ln of b to the x is not the same as b to the x. Those are 2 different things. So how would I get rid of the ln of x? So if I just had ln of x, remember the whole rule is I can raise it to the e to get rid of it, and that would just be the x, right? Remember that from way back in pre-calculus and algebra classes a long time ago? When you're trying to solve and you had an ln, you use the e to get rid of it. So in essence, by doing this, I'm getting rid of the e to the ln basically would cancel each other out. Those would be the exact, they would cancel each other out. So this and this is the same. You're like, okay, well, so why am I making this more complicated? Well, because we know E, we don't know B. All right. When you're doing an exponent inside of an ln or a log, what happens to that? It moves down in front. So this is the same thing as saying EX ln of B. Correct? Are you with me still? Okay. This right here, that's a constant. It's just like 2, like any other number. Okay, that is a constant. It is not a variable, so we do not have to do the product rule inside of that. That would be just like saying 2x. Okay. So how would I do the derivative of e to the 2x? Or e to the x squared, or e to the anything. If it's not e to the x, I have to do the chain rule. Okay. So I've got e to the x ln of b. So u is x ln of b, right? So what's u prime? What's the derivative of x? So it's whatever's left in the constant, right? So in this case, it would be ln of b. F of u is e to the u, so f prime of u is e to the u, right? Yes? Okay. So e to the ln of x, or e to the x ln of b, becomes ln of b times e to the x ln of b. Correct? Okay. What did we say this was at the beginning? That's b to the x, right? Okay. So this, so b to the x d to the x of b to the x. So the derivative of b to the x equals ln of b, actually, let me put that at the end, yeah, times b to the x. That's the rule for any exponential function. If b was e, what's ln of e? Ln of e is 1, because it cancels itself out. So if it was e to the x, that's why it's just e to the x. If it's any other number other than e, we have that ln there. So my original question was, two to the x, right? So based on the rule that we just found, that it's ln b to the x, if b is 2, b prime of x is ln of 2 to the x. So whatever number is there, it becomes ln of that, and then it stays the same after that. And like we just said, if it was e to the x, it's ln of e times e to the x, which is just e to the x. So that rule still works for e. The reason I didn't show you that one originally was the only way to come up with that rule is with the chain rule. So I couldn't show you that rule originally because you wouldn't have known the chain rule and why we could do Yes. To get the answer. All right, last problem of the night. Let's see. How long do I want to have you stay here? I want to get out of here. Let's do this one. All right. I won't try. I won't kill you too bad. I think we've already done enough confusing problems so far today. I think that's right. It's the way you wrote it and the way I looked. Yeah. Oh, so close. Place to begin. You're almost there. You got everything so far.
Just put it all there. No, that's fine. I just put it on.
Oh, I don't know. Oh, my bad. I was thinking. Oh, okay.
All right, here's the final answer. You can go if you want. You're fine.
Yeah, I was like,
Okay. So if u is x plus x to the negative 1, u prime is 1 plus or minus x to the negative 2, which is 1 over 1 minus 1 over x squared. And the other one is going to be u to the 5th, which goes to 5 u to the 4th. So y prime is 1 minus 1 over x squared times 5 times x plus 1 over x to the 4th. Year 1. All right, guys, have a wonderful night. I'll see you Thursday. That's not what I wanted. I'm gonna. I have to do related rates, which wasn't on there. So yes, we're ahead, but